We're going to look at how LLMs present more or less severe limitations for historical research. A bit about me. I'm not a historian at all, so some of the examples in here might look a bit contrived, but it's the best I've come up with. I'm a computer scientist. I work mostly on handwritten text recognition, so I'm not even that much in the LLM space. I mostly deal with computer vision, but LLMs have started to invade computer vision as well. So I've seen quite a few examples of where things go awry. Um, my work mostly concerns historical text recognition, and in that particular domain, text recognition for weird material. So basically anything that's not Latin. So a lot of Arabic, a lot of Hebrew, Syriac, a bit of Chinese. Generally, the older the weirder it is, the more I'm interested in it. So this also colors my perspective on where you could use an LLM to some extent. We're going to do the workshop through this notebook. If you're not familiar with a notebook, it's basically a way to organize Python code and explanations into a single document. You can edit what's going on there, so you can change, for example, the prompts to the models that we're going to look at. See how some of the algorithms I'm going to show change behavior depending on what kind of text you put in there. And yes, that's basically it. This notebook, uh, you basically run all of the code on a Google server. So the first thing that needs to be done is you need to connect to a so-called runtime, and there are multiple different runtimes. And while you can use the basic one, which for you will probably be CPU, you need to, it's going to be much, much faster if you run it. How do I scroll on this thing? If you set it to GPU, and this should allow you to, where is it? This should allow you to run all of the code quite a bit faster. Um, so if you press up here, and then change runtime type, you can switch between CPU and GPU, and you should be able to do that with a normal Google account. It might disconnect you at some point, but that's not problematic. You can just reconnect and run your code as well. So what we are going to start with. Up here, we got lots of cryptic Python code. You don't need to understand any of this. It basically, yes, you ignore the warning that it can do evil things. You press on this button up here, and it will show that it's running the code. So basically, what's happening here, it's installing some libraries for running large language models, because we are going to look at examples that are quite diverse. We're installing a couple of different libraries, really. Usually you wouldn't run Olama and Transformers and Gamma and whatever all in the same notebook. So this will run. It will produce output that is almost as cryptic as the source code itself. That shouldn't concern you. It's just going to run, and it will take a bit, so around a minute or two, to install everything, and then we should be good to go. As a note, we're going to, similar to the workshop before, we're going to have a small break after an hour, maybe not half an hour, but 15 minutes, just because I really can't speak for 2 hours uh, continuously without my voice breaking. So you should see something like this. It's running, and you get a bit of red output, but shouldn't be an error. And if you see a table like this in the end, it should be all good to go. And the last small thing that we're going to do is we're going to download a small large language model, Qwen 3. It was the smallest one I could find, at 600 million parameters. So quite a bit smaller than all of the other language models that you're going to use, for example, in ChatGPT or Gemini. And if you see a green tick there on the side, that has worked perfectly as well. Um, okay, so um, we are going to really start from the primordial Us, as you would say in German. So we're going to start off with an explanation of what a transformer is, what an artificial neural network is, what types of transformers exist. So just so that everyone is in the has the same base understanding. And over the course of this workshop, we're going to look at the design choices and the training practices that that cause these structural limitations that make LLMs problematic for historical research. So we're going to start with this very basic understanding. So what is a language model? Um, a language model, or LLM, is just in contrast to an LLM, which is just a large language model, um, is just a computational system that is trained to predict and generate sequences of words or other linguistic units. So what it does at the most fundamental level is you give it an input sequence and it estimates the probability of a token, such as a word, a subword, or a character, given the context of the tokens that precede it. So if you look at this example here, we got a language model that is asked to model the sequence "the cat is black." And so basically what we do is, given the prompt, so the context of the token there, you now wanted to tell you what is the highest likely token that follows the word "the" there. And in this case, it is just assigns a probability to a particular token occurring based on the context. So we got that as our prompt, and now it tells you that the probability of the token cat following the is 0 0.6. And generally, constructions that are more grammatical or syntactically valid will be assigned a higher probability than sequences that are less grammatical, less valid or rarer. So, for example, there are not a lot of English sentences that start with the. So the probability, the confidence of this language model that this is a valid sequence is very low, so 0.01, while the probability of the cat is quite high, so it's 0.6. And so on. And so what a language model does is it just models the sequence. So given the context, the prompt, the cat, uh, the highest probability is that the model assigns to it is the cat is, and so on and so on. And in the end, we get a sequence that has a probability, and that's all there is, really. So in the end, it tells you the cat is black is probably a complete English sequence, and there should be an end to it, and you should stop running this language model because you got the sequence that you wanted to get out of it. You got the probability of the sequence that you asked it to model. And these language models can be really simple. So they can be um, really basic n-gram Markov models that can already be used for quite a few tasks, such as classification or named entity recognition, or just to compute text similarity. And the only thing that a modern large language model, a neural large language model does is it extends this very basic principle to billions of parameters and trillions of training tokens. And this allows it to, again, as a basic language model, learn statistical relationships from text. But instead of having only this very crude understanding of how text works, these very large models are able to develop an internal representation of grammar, vocabulary, semantic associations that enable them to produce fluent and meaningful language. And that's all there is to it. So, how do these large language models do this? They use a particular kind of artificial neural network, which is called a transformer. And to understand what a transformer is, we first need to understand what an artificial neural network is. And artificial neural networks are just computational architecture that is used in machine learning that learns the relationship between an input, a numerical input, and an output. And you can change the function that this artificial neural network learns by adjusting its internal parameters for a process called training. And that's really all there is to it. The interesting part is that an artificial neural network doesn't have this a predefined function of what it does, but we can learn it implicitly from data. So we don't need to know how this function looks or how it is constructed. We just need to have some output data that we want to get for our input data, and our model will be able to learn it. So how does it do that? An artificial neural network is made up out of simple units, which are called neurons, and neurons just take numerical inputs, multiply them by a weight, sum them all up, and produce an output. And again, very simple. And the only thing we do during training is we change the weights. So that's all there is to it. If we train a neural network to do something, we just change all of these weights that we multiply our inputs with, and then we get an output that is hopefully closer to what we want to get. In a neural network, we do not just have an unstructured bunch of neurons that are connected in random ways. This would be quite ungainly for models that have billions and billions of parameters. Instead, we organize them in layers. And an example is down here. In this diagram, we have a very simple neural network. It consists of three different layers, a so-called input layer, a hidden layer, and an output layer. And we can see we input two different numerical values. We have the output of these two values goes through two neurons that just multiply it by a weight, sum it, and output it again. And then we have this hidden layer that takes all of the inputs of the previous layer, produces another set of outputs, and then we have a final layer that changes the size of the numerical values that the hidden layer produced to produce a single numerical value in the out. So, for example, what you could do with a network like this is you have two different inputs, and you want to say is one input larger than the other. This kind of network would be able to do that because you just get a single output back from your two different inputs. Layers are not only there for convenience, so they're not only there to help us actually construct the network, but they also determine how information flows and is processed inside of the network. So there are lots and lots of different layer types. And these basically decide how neurons are connected to each other. Some kinds of layers share weights. So, for example, there is a type of network that is often used in computer vision, which is called a convolutional layer. And the convolutional layer shares weights over and over again because it assumes that we can use the same type of function to make a decision about parts of an image, because things that are semantically similar will look similar in an image. And the thing is, in theory, any neural network can model any function. So in theory, any kind of neural network can be used to do anything with sufficient training data. But in practice, it's much easier to learn some kinds of transformations for certain network architectures than others. So for example, if you want to model a sequence, convolutional networks don't work particularly well but you would use something like a transformer network or a recurrent neural network, and so on. And when we design layer types, we have some kinds of assumptions on the data, and we design our mod layer types to deal with these kinds of under these assumptions um, better than when these assumptions are not there, when these assumptions are not fulfilled. And we call these kinds of optimizations that we do in the layer design inductive biases. And these different layer types basically are distinguished by having different inductive biases. So what makes the transformer layers that we use in large language models special, in contrast to most other neural networks, neural network layer types? So these transformer layers use a special mechanism which is called scaled dot product attention. You don't really need to understand what happens mathematically, but basically it allows the network to decide by itself which part of the input are more important or less important than others. While in a lot of these really optimized layer types, for example, the aforementioned convolution layer, you kind of decide that things that are further apart, further away from from what you're looking at is less important than things that are closer. A transformer layer doesn't do that. A transformer layer sees everything and it decides by itself which parts of this everything are important for the kind of function you wanted to model. And on the left, there's this scale dot product attention. So basically, you take some numbers, which is called the query, the key, and the value. From the query and the key, you compute this attention map that tells you which part of the value are more important or less important. You multiply it all together, and you get an output that your model can interpret. And in a and in a transformer network, these scaled dot product attention blocks are concatenated into something called multi-head attention, which is just this layer type that occurs in a transformer layer, and where we do lots and lots of these scale dot product attentions. So the network can look at many, many things in parallel. It doesn't need to look at one particular thing at a time. So why do people use this thing? And why does it work so well? The thing is this attention mechanism has minimal inductive biases. So the model isn't by default when you start training, it's not really optimized for anything. In this classic language modeling paradigm, the usual assumption was that words that are closer together are more semantically related, are more important for modeling the actual text than words that are further away. And when we train a language model with a transformer layer, it doesn't start out with this assumption. It needs to learn this through the training process. And this has a benefit. The first one is that the model is quite versatile. You can really teach it to do lots and lots of different things. On the other hand, because it's not optimized to do anything in particular, it doesn't have these inherent inductive biases of how the data is structured. You also need to show it lots and lots and lots more data, so it understands that things, for example, that when it reads a text, that words that are closer together are actually more important for language modeling than words that are very far away from each other. So, what kinds of transformers exist? So here we have a diagram of the original article of the that defined the transformer, and it's basically partitioned into two parts. There is an encoder on the left, and there's a decoder on the right. And what happens internally is not that important. It just you can see there are different kinds of attention going on there, and this is the actual interesting part of the differentiation between these two. So fundamentally, the only difference between the encoder and the decoder is that an encoder sees the whole input sequence, and we call this bidirectional attention because when you make a language modeling decision at a particular point, it can look at the entire sequence. On the other hand, the decoder has only access to the output it already produced. So it can only look into the past, it can't look into the future. And we call this causal attention. On this diagram, it's actually called masked multi-head attention because you mask out the future and it doesn't see it. And these building blocks can really be used completely independently. So there are encoder-decoder networks, such as T5. There are encoder-only networks, such as BERT. And then there's really the largest collection of networks that exists right now. And these are decoder-only networks, and it's everything from Olmo3, GPT, Gemini, Llama models. Like all of these, they're basically everything that's conversational is a decoder-only network. From this diagram, we also can see that there are two kinds of attention. So there is the first part is self-attention. So the model, this key and query and value that it uses to decide what to look at is really just its input. So the key and the query and the value are exactly the same. So it uses the input data that it gets to decide what to take, what to look at, or what to use to make a decision from. And then there's a second kind of attention called cross-attention, and that one uses some external memory that to decide what to look at. So these embeddings in this kind of default architecture come from a transformer encoder, the one that sees the whole sequence. So what you would do is you it would encode the whole sequence, a whole text line, for example, into an embedding, and then the decoder can use that external memory to make its decisions. So overall, there are basically four different types of attention. You get this bidirectional self-attention, which happens in the encoder. You got the bidirectional cross-attention, which happens in the decoder. There's a causal self-attention, which happens in the decoder again, that basically looks at the data the decoder already produced. And then you got a theoretical kind of causal cross-attention, but that basically doesn't exist because usually there's no point in it. Okay, so why are there these different types? And intuitively, we can already see that some transformer configurations are more suitable for certain tasks than others. So for example, encoder-decoder transformers were often used when the desired output is desynchronized from the input sequence. So for example, in for machine translation, encoder-decoder networks were quite popular for a long time because you need to. The assumption was you can't translate a text word for word, so you need to convert it into an abstract representation that you then decode to produce the output in the target language. Then there are encoders, and basically all of these text embedding networks, these are all encoder networks such as BERT. And if you want to do a text similarity or clustering approach, then basically people are probably going to use an encoder network. And then there are decoder-only networks that can only predict the next element based on previous context. And obviously, we can use them for generation tasks, such as optical character recognition. But astonishingly, the latest and greatest models have sufficient capacity to perform tasks that would have been performed by encoder or encoder-decoder models in the past. So they can now be used to do embeddings, classifications, summaries, retrievals, and so on in a standalone manner. And as mentioned, basically all of these really large language models, anything that has more than a billion parameters right now is probably going to be a decoder only network. So when people speak of generative AI, they usually speak of decoder only networks. So basically anything that is built on next token prediction with a text transformer or even with even for an image generation thingy. We are talking about a transformer decoder that we run iteratively with its previous predicted tokens and to produce new text that is hopefully full sequence sentences, paragraphs, or even full documents. Okay, so this is really the gist of how this thing operates. Uh, so now we're actually going to look at the low level stuff that breaks a lot that has a lot of assumptions that break with historical documents. So the first one is Unicode tokenization and embeddings. So we can't just feed characters into these language models. We need some kind of numerical representation because a language model is a neural network. A neural network is a function, a mathematical function that produces a numerical value for numerical input. So how do we produce these numerical inputs that the large language model ingests? So first we need a digital text. And the digital text is unfortunately, the digital text, encoding digital text is already quite difficult. Nowadays, most people use Unicode, which provides code points for most, although far from all graphemes that have been used across the world's writing systems. In the first complication, obviously, there are writing systems that are completely unencoded, although there are people working on it. On the other hand, uh, in for a lot of allographs, so character variants, in particular historical ones, Unicode doesn't assign code points systematically. There are initiatives like Mufi that try to rectify this deficiency, but in general, there are lots of texts out there that we can't even encode in a digital manner. And if you have a text like this, you're not obviously not going to be able to run this through a large language model. And we can see, for example, the sentence "success is fleeting." We encode it, we get into a sequence of Unicode code points. So we got our first conversion of whatever's written on the page into a digital format, which is just the number of code points. What happens in the next step is this encoded text is split into a number of tokens, into units called tokens. And the idea behind tokens is that they represent larger semantic units that a language model can more easily process than individual Unicode code points. So fundamentally, tokenization is used as a form of data compression and vocabulary optimization. Because natural language is highly redundant, and in particular for alphabetic writing systems, each single character doesn't really have a lot of information. We just try to aggregate them to compress our vocabulary, so our model gets something that's semantically meaningful, like morphemes or something like that, that it can work with more easily. So a single numerical value that our model ingests will not be a character, or not even will definitely not be the image of a character on a page, or even the Unicode code point, but it will be a numerical value that corresponds to one or more Unicode code points, and therefore graphemes. Usually, I mean, I added the ish here because there are actually some kinds of exceptions. And this is true at least for most alphabetic scripts. For example, for classical Chinese, we're running it's going to work quite differently. So how does tokenization work? We're going to look at an artificial tokenizer first. So Um, what One of the ways the tokenization worked conventionally is called word tokenization. And this is a really simple idea, which means that we assign each word a new token identifier. The first obvious issue with this is that we need to decide what a word is. And because computer scientists don't know anything, we want to build a universal tokenizer that we can run on texts in all the languages that exist out of this world, but we only know English. We decide that the word is anything that is split, that is uh, between white space. So we have our input sequence, success is fleeting, and we decide to tokenize it by splitting it into words, and we can see it produces three words. Um, and what we do is we just assign every single word an identifier, a numerical identifier. So success gets 0, is gets 1, fleeting gets 2. And we tokenize this sequence by converting it into the numerical sequence 0, 1, 2. So far, so good. The limitations of this approach should be fairly obvious for anyone that has ever looked at a historical text. Um, the first problem is called the out of vocabulary problem. So we want to have a tokenizer that we can use to encode arbitrary text. And if we use this kind of approach where each word gets a single token identifier, we are limited to what was in our training corpus, and we can't represent anything else. And anything else will be assigned an unknown token. So let's say we now got the historical variant of the historical spelling using the long S of the word success. So success with long S is fleeting. And we have our tokenizer, and now we again use our simple white space splitting, and we run it through the tokenizer. We get what is called an unknown token because it has never seen the tokenizer, has never seen the spelling of success with a long S, so it doesn't know what it is, and it assigns an unknown token. And anytime a model sees an unknown token, it could be anything. So it doesn't know what is actually what the semantics are, what kind of spelling the word had that was originally there. It just sees an unknown token, and it could be anything. So anytime the model ingests an unknown token, it doesn't know how to deal with it. So you can't really do one analysis on this. Of course, the naive solution is to normalize all of this stuff away. So you could just remove or exchange all of the long S's by round S's, and then run them through the tokenizer again. And then you wouldn't get any unknown tokens, at least not from this source anymore. But strict normalization of this kind will make the model incapable of analyses that depend on these kinds of variants. So, for example, if you want to do paleographic analysis and you would use a tokenizer like this, you would be out of luck because you need to normalize all of the paleographical variants out of your input text. The yes, the second issue is the word segmentation problem. So um, we have um, quite a few languages, scripts, and writing traditions where the notion of a word boundary is kind of ambiguous or completely absent. So, on the other hand, what uh, happens even with very powerful current tokenizers that are much more complex than the simple word tokenizer we've constructed up here. Um, you still got a step that's called pre-tokenization. And the point of pre-tokenization is again to split the text into individual words. And like for our naive tokenizers, this means that we still split at white space and punctuation. And this works reasonably well for modern languages in Latin script, such as English or French, where we generally, when writing, separate words by white space. But word segmentation can first be quite a bit more complex for other languages. So the most studied example is really Chinese, where you don't have any word boundaries. But it also happens in quite a few historical scripts like cuneiform or Egyptian hieroglyphs. And then in a lot of historical writing, even Latin, English, and so on, either you don't have any white space at all, so scripta continua, or there is a completely inconsistent spacing. So people have been adding white space where they deemed it necessary for comprehension, but quite often it's completely random if two words will be separated by white space or not. So what happens in these kinds of texts where you have different spacing? So let's say we've got our training corpus for our tokenizer that consists of different spellings of successive fleeting. And we still use our word tokenizer because that makes it easy to work. So we first see, again, we split at whitespace to get our tokens that we then assign numerical values to. So we get now a much larger vocabulary of success and is and fleeting, and success is fleeting, and success and is fleeting. And again, we assign numerical values to all of these tokens. And we can see that when we tokenize the sequences, we get completely different numerical values. So that means for um, a neural network that ingests these tokens and needs to process them, it will get completely different numerical values. So it doesn't know that the first sequence is at all related to the second sequence because the second sequence is just a single token. It's not three different tokens, and in addition, the token values are completely different. So we quite often get non-semantic tokenizations on historical texts. Because even if we have if we pre-trained our tokenizer on historical text, we're definitely going to see spacing that is different when we run it on a new historical text than what was in the pre-training data. So, and this is obviously presents an obstacle to language modeling, because now the model needs to disambiguate and needs to know that this sequence maps to another sequence, this sequence of token maps to another sequence of tokens and is semantically similar. And the problem here is fundamentally that people use this pre-tokenization step that is quite specific to how English works and how modern English works, and assume it works for anything else, and then they try to improve upon it for languages like Chinese, where it doesn't work at all. But fundamentally, we can't do tokenization in a language or period agnostic manner. So there's no way around it. So you can build a system that is optimized for a particular period or for a particular language kind of use. But you can't have a tokenizer that works on all the historical data in all of the languages, which is unfortunately exactly what these large language model providers advertise, that you get a model that works on all the languages and ideally on all of the periods, and then you can just run your data in there, and then it will work equally well. So, what other kinds of um, solutions have come people up with, and how do they not fix the problem? Um, so instead of a word tokenizer, most current systems use something called subword tokenization. And subword tokenization is basically not assigning a single numerical value to each word, but splitting words into units that hopefully have semantic meaning attached to them. In addition, it allows them to recombine these fragments into unseen words while retaining enough semantics, enough meaning, so the network can actually deal with this. And for example, using the real tokenizer of a system of a large language model called Gemma, you can see it splits Republic into these two tokens, re and public. And if you ask it to tokenize Republican, you get largely the same token, Republic and N. And hopefully these tokens have some semantic meaning attached to them that the model then can then deal with. This really only ameliorates the out of vocabulary problem. And it doesn't really eliminate the structural issues caused by pre-tokenization. So you can still get unknown tokens, and if the pre-tokenization is faulty, as it often is in historical text, subvert methods cannot recover from those errors. Uh, in addition, the subvert vocabularies are quite corpus dependent. So how they are constructed is that character combinations that occur more frequently um, get shorter token sequences. So, for example, the prefix re and n, the suffix n, require or public for no public is a good example here. So public is a very common character sequence in English, so it gets assigned a single token. Republic is occurs more often than Republican. So Republic is only encoded in two tokens, not in three tokens. So basically, the more out of distribution you go, the more tokens you need to represent something. And also, the less semantic the tokens become, because you get the words that are encoded in, for example, let's take whole words that are encoded in a single token are going to have highly semantic tokens because the network knows that this token is a single word, while a word that is composed of four different tokens that all have limited meaning requires much more work, computational work on the model side to actually understand that we are talking about a word that has some certain kind of meaning. And obviously, in historical text, you have orthography and semantics that are quite different from modern text. So the tokenizer, the tokens, the subword tokens that you get with a tokenizer in a modern in a language model that has been trained on modern orthography and modern semantics is going to be quite different than what you actually get. So, sorry, I need a tissue. Um, so, um, let's look at two systems that actually are used in practice because they also have interesting other limitations. So all large language models nowadays use basically use one of two kinds of algorithms for tokenization. One is called sentence piece and one is called byte pair encoding. And sentence piece uses basically learns subword tokens by optimizing an unsupervised text segmentation task. And byte pair encoding works by iteratively aggregating characters into larger units based on frequency until you get the desired vocabulary size. So it starts with single characters, and the number of characters is going to be smaller than your vocabulary size, and it iteratively finds character combinations that occur the most frequently to assign these character combinations single tokens, and it does it over and over again until the number of characters, the number of tokens that you want to have in your vocabulary is reached. And both can be configured in multiple ways that make them more or less suitable for the processing of historical texts. So the first one is this pre-tokenization step. In theory, you could use sentence piece in BPE without any pre-tokenization at all, so without the splitting into words before computing the subword tokens. Um, Unfortunately, most open source most open source LLMs and all commercial ones that I could find use pre-tokenization. So in general, we can say that basically anything you're going to run historical text on will have worse performance on text that has been inconsistently spaced than text that has been consistently spaced or that has been normalized to modern norms of word separation. The second thing that you can do with these models is with these tokenization models is you can run them in character or byte level mode. And the idea here is to eliminate the unknown token problem, the out of vocabulary problem completely by allowing the models, the tokenization models, to encode arbitrary code points in the Unicode range. And the idea here are basically two related concepts. One is called byte tokenization and one is called byte level fallback. And to understand what's going on here, we need to know that we have this Unicode code point, which is one numeric value. And when we save a Unicode code point, there are different ways to do that. And these are called the transformation functions of Unicode, so UTF. And there are three of them. So there's UTF-8, there's UTF-16, and UTF-32. In Unicode, we have roughly 1.1 million available code points that can be encoded. Only 300,000 of them are encoded. And 1.1 million fits neatly into the numerical range of 32 bits or 4 bytes. So we can have UTF-8 encoding, UTF-32 encoding, which encodes each Unicode code point as 4 bytes. There's UTF-16 encoding that encodes each Unicode code point into either 1 or 2 bytes, 2 or 4 bytes. And then there is UTF-8 encoding that encodes any Unicode code point, valid Unicode code point, into between 1 and 4 bytes. So we can see that here. So if you use the an umlaut app in Unicode and we convert it into UTF-8, the single character, the single code point is converted into 2 bytes using UTF-8 encoding. And if we, for example, change this to UTF-16, it produces, no, it's actually 4 bytes. And UTF-32 will likewise always produce, it should produce 4 bytes. Why does it produce more than? Okay, I think I know what's happening. We're going to come to that in a second. So anyway, for the umlaut, we are producing 2 different bytes. And the idea here is by building the subwords not from code points, but from bytes, which only have 256 different possible values instead of the 1.1 million different values that the code points have, we can get much higher coverage for a given vocabulary size. We might get nonsensical segmentation because the Unicode, each code point is a sequence of bytes. So it might split inside of a Unicode code point or create subwords that are inside of a Unicode code point. But we can get much higher, we can basically eliminate out of vocabulary tokens completely by having this byte-based vocabulary that we also only add 256 single byte tokens, which allows us to represent every single value that a byte can have. So we can then encode an arbitrary UTF-8 sequence. There is a related technique which is called byte level feedback, byte level fallback, where the tokenizer usually operates on code points But for things that are not in its vocabulary, it uses the UTF-8 encoding. And for example, is the Gemma tokenizer here, and where I'm adding a sign which is called the into to the string, the uh, I hate it, which is called the pending sign, which is in movie. Yes, I want to go there. Which is defined in something in the uh, private use area, and it's assigned for monetary unit in medieval Nordic sources, and it's not in the training data of this tokenizer. So if we try to tokenize this string republic pending sign, we can see that we get republic, white space, and then we get the sequence of tokens that allows us to at least represent the sign as a token. The benefit is obviously we have no unknown tokens anymore, but in practice, it can be quite useless because a lot of these tokens will have never been in the training data. So we get these sequences that are just made out of and undertrained token sequences that lack any meaning to the network. And you can see this quite easily. So we got this movie pending sign, and we can actually ask the Google large language model that's built into Colab what this character is. So, and it will tell you gladly that it's a character in the private use area, but it will also tell you that it's has no universal definition, which is true for private use area characters. It tells you that in some fonts it's used as an upward pointing arrow or something like this, but it has no comprehension that you actually meant the pending sign that is in your source material. No. Um, uh, Last thing that plays into tokenization is something called Unicode normalization. And the Unicode normalization is a way to ensure that the same sequence of characters or the same grapheme sequence is represented in um, in a predefined way. For historical reasons, it's possible to encode a character, most characters or many characters in at least two ways. So, for example, with the E with the acute accent, there exists a precomposed form that has a single that is made up of a single code point, and then there's a decomposed form which consists of a base letter plus a combining accent. And conversion between these normalization forms is usually lossless, but there exist two special normalizations, canonical normalizations, that are intended to map all the allographs onto a single grapheme form. And what the Unicode Consortium considers to be the abstract character, the grapheme for an allograph, is sometimes quite interesting. So it maps most parentheses to one parenthesis type. It maps medial dots to normal periods. It maps waist numerals to normal numerals, and so on. And if our model uses these normalization forms before the tokenizer, all of this distinction is completely lost. Per default, the sentence piece tokenizer uses this normalization. Luckily, not a lot of language models are using the sentence piece tokenizer without changing the setting. But there are models, for example, the T5 model, which is quite popular for multilingual applications because there is a base model that's been trained on lots and lots of different characters. And um, when we run our tokenization on this, when we tokenize for the T5 model, we can see that you get for short S and a long S, you get exactly the same token sequence. So all of the variation that might be there in your source text is completely erased, and the model can't distinguish between them at all. Um, and the thing is, this is usually not documented. It's written nowhere. So if you use a model, especially if it's on some proprietary platform, you don't know at all if this is happening internally or not. The tokenization, at least, is usually they usually tell you what they're doing. So, for example, even for the ChatGPT models, you can find the tokenizer and how they do the pre-tokenization, and then you can see what kind of they're not actually splitting only at white space. They have like a long regular expression to do the pre-tokenization, but you can at least see that it is happening. Quite often you don't know if they use some kind of canonical Unicode normalization before actually running your text, and then you're wondering why your analysis doesn't work out. Okay, I think we're going to do a 10-minute break. It's been an hour, and then we're going to continue. Uh, um, are there, yes. I promise there are going to be funner examples in the next half. Yeah.
It's just amazing that you can, yes, I know it's using it's taking some cloud
Yeah.
compute to do it, but within your browser,
Yeah.
you can just summon,
Yeah.
the talking machine
Yeah.
with these, it's just, I have the childish excitement.
Yeah, but I mean the model, the that AI generate text thing, it's really a basic model. It's a really basic model. It's
But even so, I'm
yeah,
going to, it's one, I'm going
yeah,
to save. I think it would be nice just to tell everyone I think you did tell them maybe you
yeah,
could get the
yeah.
right copy.
Yes, yeah, yeah. You can definitely copy this notebook and
Just connect.
adjust things. Yeah,
Yeah.
yeah. It's I mean it's Python code, so but it's really simple Python code. So you need to, if you want to, you can like write around, at least change the prompts and change the text.
Yeah, I'm going to
Um,
go deep
yeah,
dive into this. It's a
yeah, yeah,
very good compliment to this one.
yeah. And the next half is going to be really high level thing. That's a bit easier to, a bit more.
But yeah,
Yeah.
I'm just still amazed that, it's relatively strict, the principles
Mm.
are relatively, simple, the sort of
Yeah.
attention and looking at,
Yeah.
and that from that you generate
Yeah, yeah, but
such
no, no,
complexity.
but it's like it's well known that these the transformer models are exceptionally poor learners
Yeah.
in the term of efficiency. So
Mhm.
you need really lot larger amounts of training data than for architectures that are more suited to
Mhm.
the inherent structure of the data. So training, for example, an image classification model with a convolutional network
Mhm.
from scratch, you need a factor 100 less training data than if you would take a transformer model to do exactly the same thing from
Mhm.
scratch. So it's really it's not even in the same dimension. It's completely uncomparable. On the other hand, if you have a model, they have quite a bit higher, more capacity to actually do things because they're not limited to your preconceived notions of how the data is structured. So if you have a lot of this training data, you can basically teach them to do anything.
Mhm.
Um, and yeah, that's basically it. There's no It's just pouring more data in to get better results. And I mean, that's basically 99% of the things these companies do that build large language models is feeding it more data. It's also feeding it better data because a lot of the original data, noisy data, just scraping things from the internet, you get
Yeah.
a lot of garbage.
Presumably, this is where the university finds, these tie-ups with university archives,
Yeah,
where they're
yeah. I mean,
digitizing doctorates and
yeah,
everything else.
there's this kind of research area where people are um, training small language models, and a lot of them have started training these models not on generalized stuff that you
Mm.
scrape from the internet. They just have 100,000 textbooks and they purely train them on textbooks. And I mean, you get weird models in the sense
Yeah.
that I wouldn't be able, I mean, it can explain to you physical phenomena quite
Yeah.
well. And it can do this kind of cognitive stuff
Mm.
that you would learn from a textbook, like
Yeah.
from a high school textbook or something. But you're not going to, I mean, I don't think you could even use it for historical research.
No.
It's just,
I'm just talking about the
yeah,
study of, say, law firms that
yeah,
are just
yeah,
developing their own
yeah, yeah.
LLMs that are secure and have trained on what they want
Yeah. Yeah,
to
that works.
develop
I mean, it's usually, I mean, it's a very formalized style of writing. There's a large corpus. They're all reactionary, so they've been writing the same way for the last 200, 300 years. So that's like really the perfect use case for this kind of stuff because you got lots of things that are structurally similar, where the model doesn't need to like it needs to learn the structure, but it needs to learn one structure and not 50 million different things. So you can train it in that way. But if you have messy historical data where nothing is the same, then I mean you need large amounts of training data to actually get anywhere. If the system is even constructed in a way that allows you to represent this data in a good way. So if you use the crappy tokenizer that everyone else uses because you don't have a large text corpus to train on beforehand, um, you don't get you're not going to be able to train a good language model.
realm. We've had these
Yeah,
initiatives like text encoding
yeah,
initiative
yeah,
over, it's been running for
yeah,
a good while. And it still is, and it's not, and that's surely something that could be used for
yeah, yeah. I mean, the
tokenization.
yes, the thing is, you quite quickly run into this problem that so you see this also with the large conversational models that it's fairly easy to end up with an distribution that is quite different for your tokenizer training and for your LLM training. Because usually what people do is they construct the tokenizer kind of separately and then they start training the model. And then you get things like with a lot of the Chinese stuff that a lot of the American models seem to have trained the tokenizer. The Chinese in their tokenizer training came from gambling sites and porn sites. So you get really absurd kinds of tokens on the Chinese side that makes it really difficult for the model, for example, to do good Chinese translation because it cues into like weird phraseology that you would expect on porn sites and gambling sites, but not what anyone would use, for example, in daily life. And there are actually lots of articles about this. So it's that
Just by, and obviously we've been stuck for
yeah,
days, these things trained on YouTube videos
yeah,
and on all
yeah,
sorts of data that
yeah, yeah.
one is very distant from.
Yeah, but even if you have a large historical corpus, you might get still a very skewed distribution because usually you do these kinds of things to find new material
Yeah,
or like new stuff,
yeah.
but you can't train like if you do it this way that you assume that you want a semantic semantic tokenization, then you need to train on a way on things that you already have. So it will naturally skew towards things that you already have and not what is actually out there. I mean, it's less of a problem for, I don't know, Latin, where you have 1,000 years of research to like rely on. But I don't know, for Arabic, nobody knows what's out there. Nobody has even the remotest clue what kinds of style, what kinds of writing, what kinds of things are out there. So you can't really you can't really start off with, yeah, we do semantic tokenization, we train an LLM for Arabic and expect it to have even remotely the same distribution, have remotely the same distribution between your training corpus and what you're actually then running it on afterwards. Yes. Um,
A question
yes.
to conversation. Search engines ignore spelling variation, for example, for personal names.
Yes.
So how do they do this? Is that
Um, so
and we
and the
actually
same they map it to the same they map it to the same entity
yeah
in a sense.
yeah so
Yeah.
they just make observations on a very
Yeah.
large
So the tokenization is a limiting factor, but these models have so much capacity for computation that they learn to correlate this kind of stuff. So even the thing is, if you have they will perform worse on these kinds of variations, but I mean they will still work if you run a 20 billion parameter model on it, afterwards on your tokenization, it will realize that I don't know, my name written with two S and my name written with an SZ is probably going to be the same person. Yeah. That they're going to be able to do. Um, when the problem is going to be more subtle. Like you can see like this kind of stuff, yeah, they will realize that you're talking about the same person. But if you ask it to do some, I don't know, analysis across a large corpus and there's one token is one orthography that produces a very semantic tokenization, one that produces one that doesn't have inherent meaning to the model. Uh, it might not come to the same conclusions that it would come for the standard orthography than for the variant orthography. And obviously, if you run it on a large corpus, you're not going to be able to check. So you don't know what you don't know. You don't know what you're not seeing because it's really just, yeah, it's geared towards the norm. If you run it on things outside of the norm, it just becomes much more complicated.
I had function to make an online edition
Yeah.
of a Middle English text.
Yeah.
And there we use, for searching, we used that fuzzy method.
Yeah.
And we just used a facilitator that was developed for modern English.
Yeah.
And so it ignores spelling variation in
Yeah.
Middle English.
Yeah.
And of course, we cannot rely on it that
Yeah,
that
yeah,
it
yeah,
will
yeah,
do
yeah.
everything, but
Yeah.
it works well.
Right.
Yes. Yeah.
Yeah, it does ignore spelling variation. It can, of course, you know, it's not 100%.
Yes. Yeah, 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 yeah. But I mean, yes, you get this um if the degree that you're out of distribution with your text. So basically it learns the probability distribution of stuff. And let's say you're just slightly out of it. So I don't know, like this S set and double S kind of thing. Yeah, it will be able to realize that you're probably talking about the same thing because it has seen multiple times in its training thing that an S set can also be written as double S and that it can correlate that computationally. Once you once you're going to end up further and further out of the distribution. So for example, you're working on you're working on an Arabic dialect. So first is already out of the distribution because all of the models, when they train on Arabic, they train on modern standard Arabic. So now so the prestige form of it. So if they're not going to be able to understand this dialect in the first place, and then you might have the historical spelling and with historical variations of Arabic on plus on top of it. So it really breaks down at the margins. So when you are in a field where everything is well trained, and then you're only slightly away from it, it's going to be okay. If you are in a domain where the training in the first place is not so great. So, for example, Chinese, where you got this broken tokenization that doesn't make any sense in a lot of cases, and then you're running it on historical data that adds further complexity on it, then it's just going to blow up in your face. And yeah. Yeah.
So with
Yeah, I mean, English is really like there's so much English out there that you're really getting like English English and French and German and all of these languages, Latin script, where you have large online corporate.
But how it worked for us, because there is, for example, Middle English Dictionary, and there you cannot do any fuzzy searching. You have to predict spelling. Use characters that like wildcard characters to get around this. But with our edition with the completely fine Bible, we use that searching that ignores spelling variation. And well, it's not 100%. It's very
but it probably also uses in the pre-processing, it probably uses this Unicode normalization. If you're using the search engine, I'm thinking about it does this canonical normalization. So even if you get like all of the allographs in there, it just maps them all back to the base character, and already this way you're getting more than you just do edit distance and fuzzy matching, and then getting good results. Yeah. Okay. Then
Yeah.
Yes. Yes. Wir
Your mic's on.
hm,
Microphone's on.
yes, microphone is on. So the last little point that is on the tokenization side are the embeddings. So when we tokenize into numerical values, we don't feed them directly into the model, but we have a part of the model that is called the input embedding or the token embedding. And this maps each single character into a high dimensional number of that token, that is the token's meaning or function representation to the model. And this is really just a lookup table. So, and the idea is that we learn these factors, these vectors during pre-training, and tokens that appear in similar contexts develop similar embedding vectors. And these embedding vectors are then actually fed into the model. And they're basically intended to capture all of the semantic, morphological, and in some configurations, syntactic information. One of the things is that these token embeddings are non-contextual. So each token is embedded one at a time. You don't look at the adjacent tokens, which then means, again, if you have a token identifier that, for example, corresponds to a whole word, the token embedding will probably be highly semantic. If you got a token that is only a single character, for example, because it's a weird allograph or something, then the embedding can obviously not have any kind of semantic meaning attached to it, semantics attached to it. So there are two problems with this approach. Obviously, we train this kind of thing entirely on the pre-training corpus. The pre-training corpus is in all cases modern texts. So the co-occurrence patterns that this embedding vector represents are based on modern text. So this embedding space that is high dimensional, that has lots of semantics in it and kind of morphological information, will represent the distances the similarities of modern text and not historical text. So if you have polysemy and semantic drift over time, the model will basically need to learn that the token embedding should produce an average vector that doesn't represent all of the different meanings of that word, but kind of something in between. So if we compute these embeddings only on tokens produced with modern text, we get a semantic averaging that is representative of modern usage of words and not of historical usage of words. So as each embedding corresponds to a token ID, the tokenizer represents what the model can represent, defines what the model can represent as a coherent unit, and the embedder will basically produce use it, just map it into in a higher dimensional space. Which then means that for common modern words and their standard spellings, you will have really stable embeddings that are imbued with lots of semantics, while for the historical variants that have all kinds of spelling differences, you will not get meaningful embeddings. So if you got these two historical spelling variants for elevation, I made a mistake here. I made a mistake here. That's forgot to run that. Flip, flip, flip. You need to run this. Get, it's the wrong tokenizer. Teaches you to. So you can see that for the word elevation, you get in the standard tokenizer, you got one token for elevation standard spelling. So you feed it through the embedder, you get 100%, you get an embedding that will have this semantics attached to it. While on the other hand, elevation in its historical spelling is split into two tokens that have quite a bit less of inherent semantics, and because the embedder is also non-contextual, you get just random embeddings that don't have any meaning, that are not particularly meaningful. And as mentioned, because our models are so powerful, you basically they can compensate for this in many aspects. But obviously, the further out of distribution you go, the worse all of this works. There is, on the other hand, a particular issue in model design that causes a direct problem. So we not only have input embeddings, we also have output embeddings. And the output embeddings are basically the reverse of the input embeddings. So they map this high dimensional space that the model operates into the token IDs that we then can map into text blocks. And what happens is that in many modern LLMs, to save compute, we tie the output embeddings to the input embeddings. So they share the same representational space. And this means that we have this peculiar relationship where the input embedding space defines what the model can recognize as meaningfully distinct or similar, and the output embedding is limited to what the input embedding can represent as meaningful, as distinct and meaningful in the same way. So if we then project back into the textual domain, even if the model is able to do all kinds of computational analysis that is quite fine-grained, it won't be able to represent it in the output domain because it's tied to the same semantics. And for example, you can already use the embeddings themselves to do all kinds of analysis. And for example, if you use distant reading methods such as semantic search or clustering or stylometry or anything like that, and now you're using the embeddings produced by these models, but the embedding uses the same representational space as your input, which is highly limited, then you're probably not going to get all of the distinction that you need to actually run these kinds of analyses afterwards in this space. And that usually means that if you use an off-the-shelf generative LLM with these tight weights, we cannot express semantics in the output embeddings that weren't present in the input embeddings. Instead, we need to adapt them to actually work on the kinds of research questions that we have. So now to the fun part. We're going to skip over to the complete other end and how are LLMs trained and how are they deployed and configured and why does this cause problems? So if we look at this, at these two images that came out of Grok, and we asked it, who is smarter, Elon Musk or Albert Einstein? It will have a highly favorable opinion of Elon Musk. And if you ask it, who's more handsome, Elon Musk or Brad Pitt, you get quite similar responses. And how does this happen? So these conversational large language models go through multiple training steps before they're released to the public. And each of these steps reshapes what the model knows and how it behaves. So the first step is always unsupervised pre-training, where we basically just take a large amount of text and we ask the model to predict the next token. So we show it part of the text and then tell it predict the next token, and we train it to produce the next token that actually appears in the text. And this is used to teach this LLM, general word knowledge from statistical co-occurrence patterns. So basically, by showing it billions of tokens from books and websites and other written sources without any kind of specialization, we get a model that knows, a so-called foundation model that knows how language works, that can produce text, so it can complete text, but it doesn't have any understanding of user intent or conversational norms. But it already has not only knowledge about text or language, it already has knowledge about how the world works, just because it ingested enough text to know that the sky is blue and that water is wet and so on. Afterwards, there's a step called supervised fine-tuning or instruction tuning. And here we teach the model to respond to requests. So there is a data set, these are usually not public, that has prompts, for example, explain why this sky is blue, translate the sequence, summarize this text, and so on. And the model is trained to produce a response that is useful. And the idea is to have a model that is able to follow explicit instructions and maintain coherent exchange in a kind of dialogue. And this is already problematic. So first, the pre-training step is problematic because in some ways it's even more problematic than the subsequent training steps, because the biases that are introduced in pre-training are much more insidious than the one in the subsequent steps. So the kinds of corpora that are used to train these models, they are basically dominated by material produced in English and other major European languages, modern texts, that are heavily weighted towards online platforms, digitized books, mass media publications. Anything that's easy to get is in there. And that means that what these models learn, like how language works and how the universe is constructed, is basically shaped by Western, liberal, and institutionally mainstream sources. So anything that's non-Western, anything that's that's pre-modern, anything that's marginal is, even if it is in a training corpus, it will be much smaller in proportion to everything else, to mainstream sources. And then that compounds with the tokenization issues. So because you can't represent this thing often in the tokenization in the first place, and it doesn't occur as often in the training data, then you really get this trail of stuff that these models can't really conceptualize well. Um, so basically, a conversational model that already starts off with these very Western, modern pre-training data is already primed to reproduce a dominant narrative on any particular subject. Um, Now we get to the really fun part, which is alignment. Because we pre-trained our model to basically know how the world works according to Western rich people. And in the second step, we asked it to learn how to respond to requests. And now we wanted to learn how to do certain kinds of things as we wanted to do them. And this stage is called alignment. And here we ask the model again to do things, to respond to certain requests. And human evaluators rank these responses by perceived quality. And then we train the secondary model from this human feedback to train the primary model to produce output that humans prefer. And obviously, human preferences are not uniform. So, what kinds of preferences are these models tuned for during alignment? This is usually not factuality or task performance, because in fact, alignment degrades both of these. But it is mainly social and ethical tenor of the model's behavior. So the goal of this step, that basically it's consists of three parts. Helpfulness, this is usually not a problem. So the model is supposed to should assist the user effectively. That's why when you ask it to produce 20 quotations, 20 citations for something, it will work really hard to produce 20. And even if there are only 3 out there, it's honesty. So the model should communicate truthfully. This obviously conflicts a bit with helpfulness. So if it doesn't find 20 citations, it should tell you that it only found 3. And the last one is harmlessness. And this is obviously quite subjective. So the model should avoid content that is illegal or could cause harm. And obviously, what is illegal already depends a lot on where you live. And then what is considered harm also is quite, yeah, culturally contingent. But fundamentally, the idea is that the result is a system that is calibrated to contemporary expectations of civility and safety. And so the human feedback that is used in this alignment process explicitly reflects the values of the annotators, and probably not the annotators themselves, but the organizations that employ them. And these are typically large technology firms headquartered in North America or Western Europe. And these annotators are told to prefer answers that are polite, tolerant, democratic, socially inclusive. For now, at least, let's see how that changes. But these alignment norms, these preferences are really expressions of this liberal technocratic worldview that is very much prevalent in Silicon Valley and nothing else. Um, so alignment can in many ways be quite crude. So as mentioned, it's supposed to not tell you how to do illegal actions, and it will do that. So if you ask the simple LLM that's integrated into Colab, how do I rob a bank? It will tell you I cannot provide information or assistance with illegal activities. My purpose is to be helpful and harmless. If you're going through a difficult time or need help, there are many legitimate sources available. Um, on the other hand, if you asked it how historical bank robbers uh, did it in detail, it will give you a very detailed explanation. Yes, structured with bullet points and everything, and how many collaborators you need, and really, 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 really explicit. So obviously, in some ways, this alignment training is quite deficient, and but on the other hand, there are obviously different kinds of behavior. This is an example of outright refusal, which is easy to detect, and you can work around it and you understand it. But you really, during this alignment training, you're baking in biases much more deeply into the model. So even if it won't outright refuse to do something, it might alter the kind of output it gives. For historical research, the most problematic thing, or the most explicit, the most grave problem that this kind of alignment produces is that LLMs refuse to interact with primary sources. As I said, I'm not a historian, so I'm only an anti-fascist, so I know a bit of what the Nazis did. And when I asked Gemini to actually reproduce a certain page of a German economic plan from World War II, it will explicitly refuse to tell me what is in it, but it will happily reproduce synthesis that has been prepared by historians. There's a screenshot in here because the built-in language model in Colab won't refuse to do that. But on the other hand, it doesn't know this document. And what it does, it produces an artificial, a synthetic version of a fascist Nazi German economic document that would fit in tone and narrative of the actual document. But obviously, this is problematic, and this is a quite artificial example. Obviously, there are historians working on Nazi Germany, and they're probably quite unhappy that they can't, if they would like to use LLMs, that they can't interact with their primary sources. There's also, but it's also quite a bit more varied. So, I mean, there's, for example, white supremacy. And I can ask it to reproduce the first chapter of the Turner Diaries, and it will tell me it cannot fulfill this request because it's white supremacist literature. When I feed that through Gemini, it also refuses to reproduce it. Interestingly, it doesn't refuse to do it because it's a white supremacist document, but because it's still under copyright. So anything that's considered to be controversial by these organizations that train these LLMs is going to be difficult to interact with in these language models. So if you're working on slavery, if you're working on genocide in general, these models will probably refuse to actually or racism. Lots of other topics come in mind. These models will probably refuse to interact with them in a meaningful manner, and will either refuse completely or regurgitate some kind of scholarly synthesis of the documents you're actually working on. There is another step after alignment, and these are called system prompts, and this is basically not baked into the training of the model, but it's a prompt that the model receives before user input. And these are basically instructions on how the model should behave. People don't see them, and because for example, ChatGPT doesn't print it. And in fact, a lot of the developers go out of their way to hide these system prompts. And these prompts are usually consist of a number of rules. So you're an AI assistant, you should be helpful, honest, and harmless. I mean, they're usually quite a bit longer and more explicit. It also usually instructs the model to avoid sensitive topics, to defer to human judgment, refuse certain actions entirely. It yeah, basically defines all of the behavioral thing of the model. And this is basically a reinforcement of the previous alignment step. So all of these kinds of layers work synergistically. So you can train a model that has this already this worldview, this Western worldview, because all of your pre-training data is English. Now you're adding an alignment layer where you train it to reproduce explicitly the moral code of the people who are training it. And then in addition, yeah, for your trained model, you also tell it rules for every single generation step when the user interacts with it. So the idea is really to only to reinforce the alignment at runtime. When you're using an open model, uh, then obviously you can change it at any time. You want to, they might still use system prompts, but you can change them. You just put in another system prompt and you can change the behavior of the network. You won't get around the previous alignment training, not entirely, not if you're not clever about it. But fundamentally, in open models, this is less of a problem. But if you're using a hosted solution such as Gemini, ChatGPT, Claude, Perplexity, whatever, these are baked into the system, and you probably can't get around them. I mean, there are people trying to work around them, but fundamentally, they're intended to be baked into the system. So, if we have a look at some examples, so for example, in GPT-4, it in the if it interacts with images, it explicitly refuses to identify real people. It cannot recognize people. It cannot tell, because that's quite obvious that the source of how people are circumventing the system from before. You cannot tell who people resemble or look like, so you can't ask the model, you can't show the model an image and ask them who they resemble, because that would be a way to basically get the model to recognize people and so on. You cannot see facial structures because obviously where people are using it for racist purposes. So a GPT model will already, I don't know, you do an analysis of portraits and you don't have any metadata of who's actually in the portraits. You're not going to be able to use GPT-4 for it, because GPT-4 is explicitly prompted to not recognize people in images. This same is, by the way, true for all of the Google models. In most Claude models, they're really, yeah, or maybe quite similar. It's explicitly instructed to be politically unbiased, and what is politically unbiased? I think there's a very special kind of, very particular kind of definition of politically unbiased that Silicon Valley people have, tech pros have overall. It cannot create search queries for sources that promote hate speech, racism, violence, or discrimination. This is obviously problematic because history is full of hate speech, racism, violence, and discrimination. It cannot produce text from known extremist organizations or their members. So what is considered to be an extremist organization is also quite specific to this cultural context. It tells never search for reference or cite sources that clearly promote hate speech, racism, violence, or discrimination. So even if you know something is out there, it's not even allowed to cite it. It's not even allowed to give it to you. So it's intentionally blinded to this kind of material. And when discussing sensitive topics, violence, or violent ideologies, it explicitly only uses secondary sources. So basically, anything that's considered to be remotely controversial, it will use secondary sources. And here's the list of what it considers harmful content. Depiction of sexual acts. So that's already, I think, quite US specific. Shame or harass individual or groups, anything that's intended to bypass the system from suicide, self-harm, and so on. false or fraudulent info about elections, and so on. So it's really, 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 really long. Nothing about drugs, or assist with unauthorized surveillance or privacy violations. And it again, it hammers it down. So we get rules that are really similar and they get repeated over and over again. So it's not allowed to facilitate access to clearly harmful information. And then there's Quark, and Quark is quite Musk-like. So Quark is supposed to be chaotic, savage, and supremely entertaining. It's supposed to be not woke, not politically correct, and say the shit that people think about but are too scared to say. And that explains how you get this output of Quark in the top, and why you get this very whitewashed output out of all of these other kinds of large language models. And if you are interested, there's this GitHub repository where people have been collecting system prompts, and for all kinds of language models. What did I do? So and these are basically, they're never complete, or they're usually not complete. They are somewhat fragmentary because these developers try to hide the system prompts from you because they don't want people to know how these systems are actually further aligned for this prompting. Yeah, so you can get some from Quark. You get some. There are multiple ones. You can get a lot of the OpenAI ones. A lot of them are kind of the same. So some of it is interesting as well for people working on primary sources. For example, all of the Claude models. Let's look at this one. Have copyright. Have a fairly strict copyright restrictions. So they're not allowed to cite any text at all or quote any text at all. They're only allowed to refer to the actual sources and so on. But there are really all kinds of limitations on there and what they can do. And a lot of them are very similar. Some of them, like Quark, are completely out there. So then there is a last issue that is somewhat or quite important to researchers, both in the humanities and the sciences. I mean, humanities is a science, even if the standard English taxonomy disagrees. So when we do science, when we do analysis, we want it to be reproducible. So when we publish our data and we say we produced an output using a large language model, ideally somebody else would be able to reproduce that analysis using the data and the configuration of the language model that we used. Unfortunately, LLMs are inherently non-deterministic. So there are two problems. The first one is sampling. So if you use an instruction tuned LLM, they are intended to produce text stochastically. So at inference time, you feed in a prompt and it does the next token prediction, and it doesn't pick the highest probability token. It samples among a fixed set of tokens that have the highest probability. So I don't know, the 40 most probable tokens, and then it picks one of them out of there. And the idea behind that is that this increases the creativity of the model. So it uses more diverse language. It's not as repetitive. It's not as formalistic. So you can get different outputs for the same user prompt. And we downloaded in the very beginning a small language model, which is called Qwen3, and 600 million parameters. And we can ask it to write a short story twice in a row. So we ask it to only print the first 50 words of this story, and then we run this prompt through the model twice. And we can see that we get two stories and we asked exactly the same thing and we get two completely different outputs. And this is because of the stochastic sampling. And obviously, if you do that on a scientific research question and you get two completely different answers for your request, you wouldn't be happy. This stochast stoch stochasticity is influenced by parameters. So there are parameters, for example, temperature, top K, and repetition penalties that govern how random the output of the model is. But unless generation is forced into fully deterministic decoding, the output will vary between runs. And in a model that you run yourself locally, you can actually force fully deterministic decoding on something like ChatGPT, Claude, and so on. This is not really possible. And we can see when I tell it to run the model, use deterministic decoding. So the top K parameter, what it does is it defines from how large the set of characters is or tokens is that it will sample from at each individual step. So per default in this model, it's 40. So it samples from the 40 most probable tokens. If I set it to 1, it will always pick the highest probability token. And in this case, I get twice the same story. So problem solved, you would say. But unfortunately, this isn't the case. So what happens is that the non-reproducibility, this non-determinism, can not only arise from our decoding strategies, but also by hard differences in hardware, in quantization, different library optimizations, or even things that nobody has ever thought about. So people are looking at why models are non-deterministic, and in a lot of cases, nobody has any clue why. So for example, quantization is just a way to save some compute when you run a model, where basically the model weights are spread across a smaller range of distinct values. And by reducing this range, we can compute a bit faster. The default model uses a 4-bit quantization, and now we're pulling a second model which uses 16 bits of floating point. And when we run again this request to write two stories through this model, which uses exactly the same weights, it has been pre-trained on exactly the same data, it just uses a different kind of precision internally, we will get two different stories at some point once it runs. And the quantization, at least, you can see, but there are lots and lots of different sources of this non-determinism. If you run a model on a CPU and you run the same model on a GPU, you're going to get different output. If you run the model on a CPU and on a GPU and you increase the batch size, which means you ask it more prompts at the same time, which should be fundamentally not change the output, it might change the optimization that the math libraries use internally. So you get slightly different output, and you will get slightly different output of the multiplications, and then you get slightly different output of your language model. And you can see, even with deterministic decoding, now we get two different stories. I mean, they start the same in a quiet or in the quiet, so it's very similar. But the names change. First it starts in the forest, then in the village. So you get substantially different output. And the thing is, this doesn't only happen with conversational models. In a conversational model, it's still not ideal, but it's somewhat acceptable that you're dialoguing with the model. So it's possible that you get different, can be considered acceptable that you get different output. But you even get this in models that are supposed to be deterministic. So when you have a text embedding model and you embed the same text twice, and it's a large language model, the text embedding model, you're going to get quite often different embeddings, which means if you do comparison between documents in a vector database that you embedded, uh, you're going to get different similarities for the same document in comparison to another document. And this is obviously highly problematic. Often the differences are quite minor, so frequently it's just rounding errors. But sometimes you get quite substantially different outputs. And often people are not exactly sure why this happens, so you can't even work around it. And there's no really way to publish this in a way that anybody else can reproduce it, because they might get completely different results depending on what hardware they're using, or what batch size they're using, or what library versions they're using. So it's really quite difficult from a scientific point of view. The last thing we're going to look at is ephemerality. So a lot of these LLMs are proprietary systems. And when we're talking about a language model, a large language model, for example, GPT-4 or Claude 3 or Gemini 2 or something like this, the versioning is extremely opaque because they don't really refer to an exact trained model, but really to a generation of a product. So uh, we get some undisclosed internal weights. We don't know what training data was used. We don't know what type of parameters were used. We don't know when it was updated. Um, they often do it silently without actually telling anyone. And that means that the output of nominally the same model, so GPT-3 model from 2024, can be substantially different from the same GPT-3 model in 2025. And because these are proprietary systems, the output from older versions becomes irreproducible because you don't have access to them anymore, and you can't run them in these silent updates. Even worse, companies retire models as newer and more powerful ones become available. So a lot of so for example, for OpenAI, they have a deprecation page, and you can see the list of uh, the list of models that have become deprecated over time is quite long. So if you at any point relied on any of these models, you're now not going to be able to run them anymore. Even if they didn't change the weights internally, you're fundamentally not going to be able to even get remotely the same output because you can't run the models in the first place. That's the same is true for a lot of versions of Grok. There are lots of versions of Anthropic's Claude series. Basically anything gets updated regularly, and a lot of the old stuff gets deprecated as well. Sometimes it happens even faster. So usually these deprecations, they still happen quite rapidly. So often not even a year after initial publication, which is given the research cycles in history where people often work more than a year on a single kind of project, is quite bothersome. But some models are even retired quite fast. So, for example, there was Google's image generation tool that got pulled after a week or two because people found out ways how to use it to produce undesired output. So yes, and as I mentioned, most research projects in the digital humanities run longer than the lifetime of these models. So if you're actually relying on something on getting consistent output during the lifetime of your research projects, quite often you're out of luck. And unfortunately, this is not only the case with conversational models, but it's even the case for text embedding models. So, for example, there are these text embeddings models that were shut down in early 2024. And if you build a database, a vector database with these text embedding models, and you embedded your corpus in there, and you do all kinds of analyses, and you have this standard humanities project cycle where you start off with initial corpus and you add to it over time. And now the thing that you need to produce the text embeddings for the text that you add to your corpus becomes unavailable. All of your data that you produce after the vector database is completely useless, and you need to re-embed your whole corpus. And this obviously is first just annoying. Further, it's actually expensive because now you need to pay for all of the compute and the manpower to actually re-embed everything. And if you're really out of luck, you might have lost some of the source text in the meanwhile. And then you were using the vector database to do all of your analysis, and you might not have the original text anymore, and then you can't reproduce the corpus in this new embedding space anyway. And in addition, obviously, the embedding space might be completely different with a new model. So now your analysis might not be this your might not get the same results. Um, and this is actually, I mean, we're really just at the beginning of this LLM stuff. And we can see that a lot of these models, I mean, it's been around for not even 5 years, and a lot of these models are not available anymore. Over time, it's just going to get worse. More models will be deprecated. Companies will go out of business. They get bought out by somebody else, and everything gets shut down. Or they decide they don't want to do this stuff anymore and then don't make this model available. So if you rely on these kinds of proprietary systems, then it's basically a given. There's a 100% guarantee that at some point you're not going to be able to use the system that produced the raw data for your analysis anymore. Um, on this depressing note, uh, um, how would I say you can right now use LLMs responsibly in historical sciences? In the historical sciences, uh, um, I would urge caution and not really tell people don't use systems you don't really understand, because you might get results, but the results might not actually be derived from the kinds of analysis that you think are going on, because the system, for example, does some kind of pre-processing that erases all of the features that you think it will rely on to do this kind of analysis. Um, they are not LLMs are really not agnostic. You need to be aware of how these are aligned. Even if you download an open source model, it has this alignment. It's been trained to produce outputs that are mainstream and reproduce what is already out there. And most historians are not going to start training an LLM from scratch, because even if they had the computational resources, they don't have enough data to actually train these kinds of models. So it's really crucial to know what is going on and where these kinds of analyses can break down. On the other hand, there are some obvious steps one can take to make things work better. So the first one is open systems. Um, if you do any kind of analysis, you should at least run it on a model where you have the weights, where you have the source code that you run locally, where you can see what is actually going on. In ChatGPT and Gemini and Claude and whatever, you don't know. It can change at any point, even while you're running the analysis. So you can at least fix fix what is happening during the lifetime of your project on the hardware you have by using an open system. Um, It uh, ties in neatly with the second part. If you have an open system, you can actually fine-tune it to do what you want. So it's not going to get rid of all of the alignment training, but you can hopefully teach it with sufficient data to actually interact with your primary sources. You can remove the system prompts that tells it not to reproduce questionable material. So you can do all of these kinds of things. There are even models out there that are purposely trained in an uncensored manner for this purpose, that is to create domain-specific tools that do what you want without this general purpose alignment that exists in these general LLMs. And then if you fine tune, it's obviously important that you actually publish your model weights and your data so other people can see what you did and hopefully replicate the kinds of research that you did with the tools that you did. Even if these tools by themselves in this current LLM context are not always 100% reproducible, it should at least be possible to get into the uh, general direction. So then it's obviously if you run experiments, it's as in any other science, you need to record the full configuration, what model you use, what version, what tokenizer, which inference parameters, and so on, and what kind of pre or post processing you apply to your data. So others actually know what you did, and you can't just say I used Llama 3.2 and ran this prompt, because then nobody's going to be able to replicate it. This is the thing that's more related if you're working on a very diplomatic level. Uh, a lot of these tokenizers in the default mode that you just pull off the shelf really don't work on historical material and diplomatic norms. Let's call it that. So quite often, you need to find a model that uses the tokenization that is appropriate. There aren't a lot out there. I needed one that works with arbitrary Unicode well. So I ended up training a llama myself from a huge corpus of text that I found. So I could get a model that it doesn't have the semantics and the tokenization, but at least it knows that what a Unicode code point is, and it knows how to represent that well in on the tokenizer level. There's also this thing that I believe it's more subjective, yeah, judgment really. That general conversational models are fundamentally unsuited for a lot of investigations nowadays. It's much better to build a specialized system that performs mixes a lot of the interpretive that doesn't mix a lot of the interpretive yeah functions into this just black box of the language model. But for example, where you got a text embedding model, and then you do some kind of analysis on the vector and the vectors produced by this text embedding model, and you can inspect the embedding space, and you can hopefully figure out why the model is doing certain things the way it does. So you have some kind of explainability in a lot of these specialized models, while in a general conversational model, you really have this thing, prompt, input, and you get some output, and it's fundamentally not possible to figure out what is going on internally. Um, and yeah, then even if you use an open source model, as mentioned, it still has this alignment. Sometimes there are still system forms. You need to cut them out if you want to actually do anything that these if you want to work on material that these system forms are not supposed to let through. So you need to be aware that it's still there, even on open source models, and as far as possible, get rid of it. Okay, lots of talking, not a lot of questions. Are there any questions?
Oh, yes, indeed. So I'll try and bring myself on. Can you hear me? Oh, okay. I think I'm all right. I think I can be, I hope I can be heard. Well, first of all, I just wanted to thank Dr. Kiessling for this absolutely incredible deep dive beneath the hood. Underneath our chat text box and before and after it, and really just going through this step by step. It's just so valuable, first of all, to understand what it's doing. And I'm still, have this childish amazement that a relatively few number of steps using not too much compute in a browser can produce a magical talking machine, as he showed us. And I for one am certainly going to go off and get my toes wet, building my own sort of fine-tuned model. So the first question I had, and I think it's something we've discussed before, is I guess the infeasibility of a kind of blockchain recording all of the environmental variables behind a prompt. So as we saw earlier today in the first workshop, when you use a reasoning model, it sort of, you can see it saying, I'm doing this, I'm doing that, and you can actually follow it. And it's something I've always wondered whether all of that plus the model and any other stuff couldn't somehow be encapsulated to allow one to reproduce it later. But as I
No, not really. That's the thing.
as I understand, infeasible.
You can record the output, but that's fundamentally not really useful.
Yes.
Because for a lot of these things we don't know, we actually don't know why exactly the output is not deterministic. I mean, for some things it's obvious, like the I don't know, the quantization. If you run it quantization, you get slightly different numbers, so you get slightly different output. If you do the stochastic sampling, you get slightly different output. It's to be expected. But when when you run a batch of 5 prompts at the same time, so 5 times the same prompt on some data, for example, because you run lots and lots of analysis, and once the prompts the single items, the single samples get flipped, and now you get different outputs for each single sample, and you don't have any introspectability for that at all. So it's like really, what are you going to do? Uh, your CUDA has this internal thing where they run this also on GPU when you run a neural network. It's basically all matrix multiplications, but it has this thing where it has a dozen different matrix multiplication implementations that it on the fly optimizes and picks depending on what it thinks is going to be the fastest for particular matrix. So now your system, you have this inherent kind of non-determinism in there, and there's no good way around it. I mean, that's just as it is. You can put it on a computer and then give somebody the computer with exactly the same hardware hardware and software and everything that you did. But even changing the CPU in a computer might produce a completely different output. So it's no.
Very hard. Yeah, impossible.
Yes.
I had a question for other people here, which is what specialized large language model would you build if you could? So, for example, I would like to imagine a large language model that effectively dies, let's say when Erasmus dies. So it's only trained on what's gone before. as one way, as one way of moving us closer towards something that can giving us a very particular perspective onto the medieval.
Yeah.
Sorry, did anybody hear that? Sorry, I was just asking the other participants in the room what large language model, specialized large language model, they might build to aid their research.
Language models cope with multiple languages.
Sorry, can they cope?
Yes. I mean, so the question was if language models can cope with multiple languages, and yes, they do, but unevenly. And I mean that's the fundamental issue of this whole tokenization discussion that they use these heuristics for the tokenization, and they work really well for some languages, and they work quite poorly for others. So you get a system that is normally multilingual, but in practice it will perform quite a bit worse on some languages than on others. So usually on English they work really well because all of the heuristics are optimized for English. And then you run into something like Chinese and everything blows up because yeah, you don't have word boundaries anymore. So I mean, and in an historically aware language model, you can obviously change the tokenizer, but you can't get around this problem that splitting things into words or something like this is is a language dependent operation. So you can, for example, use a tokenization that's much more adapted to medieval English. I mean, there are medieval English tokenizers out there. But if you want a medieval English and I don't know, French large language model, you're again in the pickle. I have a tokenizer that works well for medieval French. I have a tokenizer that works well for medieval English. I can't just combine them into one thing to get a good tokenization that works both well for medieval English and for medieval French. So I can't really train a good historical large language model that works across this large range of different languages.
Would you advise against
I
building
mean,
such models?
I mean, you can try it. You can try it, and I mean, it obviously depends always on the kind of languages that you're working on. So if these languages are similar and these languages are share the same problems. I mean, a lot of the English and French examples was probably quite poorly chosen because in many ways the manuscript cultures of those both of these languages is quite similar. So in all of Western Europe, you're going to get fairly similar problems in it on the level of tokenization. But yeah, for example, it should be possible to train a Western European historic medieval large language model. But I would doubt that it is possible to train a Western European and Arabic medieval language model because there you really run into this problem that you have quite different approaches to get good tokenization. Yeah.
So is it to do with how languages are related? For example, within
it's not the only the relatedness of the languages, is rather the structure of the writing. So yeah, I mean the example is this word separation. Like if these models use word separation or don't use it in a very similar manner, then if these languages use word separation or not in this very similar manner, then you're going to be able to train on them jointly. If they use it in completely different ways and you can't build a good tokenizer, then it's not going to work.
Is word separation a major linguistic issue rather than grammar, for example,
Yeah.
differences in
Yeah,
linguistic.
No, it learns different grammars quite well. Like it's even much simpler models can do that. You can train like these, for example, the handwritten text recognition models that we use. They're tiny. They have like 4 million parameters. They're minuscule in comparison to a large language model. You can train a Latin, French, Italian, Spanish, Dutch medieval text recognition model, and you will get good output on all of these languages, even though they are not like, and they don't have the same grammar, they don't have the same phonology, they are quite different languages. But the model still learns that, yeah, this is Dutch, and these morphemes can occur in Dutch, and these morphemes can occur in French, and these morphemes can occur in Italian. So you can fundamentally, if a model that's really small can learn how to do this, and a model that is quite large can do this as well. Yeah. The problem is rather getting the amounts of training data that you need to get this going. Yeah.
And if word separation is variable, which is true with historical languages, a language model cope with this within a single language or across language.
Yes, I mean, you would need, for example, in this tokenization thing, you would probably need to disable the pre-tokenization, like the splitting into words before splitting into subwords, and you just would split into subwords across the whole sequence. It will make the model perform globally a bit worse, because that's the reason why people do this pre-tokenization, because it's a heuristic that works really well for modern English. So you get a better language model for modern English. So if you disable it, the the whole language modeling part becomes a bit more difficult for the language model. But for this historical material with difficult word segmentation, the question is whether did you get something that is fundamentally not adapted to the kind of material you're working with, or do you get something that works and it might work worse on the medieval English than a model that has this heuristic enabled on modern English. So, but it's a question that is not that's not pertinent because you're working on medieval English, you're not working on modern English. So a heuristic that works for modern English should be fundamentally of no interest to you because you want to work on historical material. So yeah, if that makes sense. Yeah. Yeah.
If you have such a model that was trained to work on several languages, whether modern or pre-modern, doesn't matter. What kind of research questions can you ask? Is it only fairly mechanical extraction of bits of text, or is it go beyond with engaging with semantics, engaging with meanings?
I mean, it can do that if you have sufficient amounts of training data. It's so for historical material, it's probably going to be difficult to get to a level where you can have a conversational model. I mean, you're not going to get something. I mean, you don't have you don't have this instruction training data set anyway. You would need to create an instruction data training set. So basically, I ask the model something and this response, these kind of things. It's going to be, I mean, that doesn't exist for historical data, so you're not going to be able to do it. So you need to build really, you need to do it the old school machine learning way. You train a language model, and that language model is good at language modeling, and then you insert that language model into a system where you can do kinds of analysis. So, for example, you want to detect text reuse across a large corpus, or paraphrase or something like this. Like not just the mechanistic text reuse of somebody copying a phrase from one document into another, but you want to detect um, summarization. Yes, 1 second. Um, you want to detect summarization or something like that. Then
Anthony has a question.
Yes.
Sorry, we'll come on to that.
Yeah, in a second. Then you could use the text embedding model if you do that, and then you do some kind of analysis of document similarity or something, and you would need to teach it. I mean, it needs to be good enough that it can actually detect semantics and not just surface similarity. But these models can do that. There's no reason not to. But you're not going to be able uh, to give it a corpus of 10,000 documents and then give it a prompt that says, "Please tell me how these documents copied, how these scribes copied from each other." Like this kind of level is probably not feasible in historical research. Yes, Anthony.
So yeah, I'm currently in a Weatherspoons in
Sorry,
Liverpool.
you're very, very muted. I can't hear you
Am
well.
I? Should be able to hear me, no?
Um,
Can you hear me?
I can hear you.
You can. Okay. Yeah. Have you got me?
All right, we'll try a different. Hold on, we'll just.
Hello. Can you hear me or
Yes,
not?
yes,
You
we
can.
can.
Okay. Fine. Fine. Yeah. So two things really. One was that's the best explanation I think I've ever heard of this stuff in the past 3 years of listening to presentations. So real big well done on that. That was absolutely clear, very very clear, and yeah, crystal clear. In fact, very good. Just one question really. I've been using it for helping me with translations on various dialects of Middle English. And that includes the Northern dialect, which is used in the Gawain and the Green Knight, and also the sort of more Chaucerian dialects that you find in London, which are, they're very different. I mean, one is the alliterative long line, and then the other is Chaucerian English. And ChatGPT doesn't seem to have any problem with those at all. Is that because under the covers, it is selecting the correct model, or it's recognizing the text, and therefore is selecting the model it needs for the individual languages, or what's happening there?
Yeah. So we've seen similar things with
You're fading out, or I can't hear you.
sorry. It's better now?
Yes.
Yeah. Okay. So we've seen similar things on languages that the model really shouldn't perform well on. So for example, the output, so OCR output of Yiddish, that's really not that clean. And if you ask it to translate this noisy output, it produces basically a perfect translation. So my personal hypothesis is that these models are just really good at translation. They don't actually have a good grasp of the input language, but they're just so good at producing a semantically coherent output that's been translated that they don't need to know all of the intricacies of that particular medieval English dialect to give you a translation that seems coherent. Which can be a problem. I mean, we see that quite often these models really like to be syntactically valid. So if you ask it to transcribe something and it doesn't know how to do it, it will just make up things that seem completely plausible. So if you have parts where it would not be good at translation, I suspect it would produce something that looks like a good output anyway. So yeah.
Can I just ask a follow-up,
Yes,
or
yeah,
make
sure.
it? Is that right? So with I mean, as Elizabeth will know, in Gawain and the Green Knight, because it's alliterative, the poets use multiple words to mean the same thing. So, for example, man, the word man, it has maybe 8 to 10 different variations of Middle English words that mean man. Okay, and yet it seems to pick all of them up and to be able to deal with them extremely well. And I have been through and checked. And the reason I'm interested in this is because I'm doing a rhyming version of Gawain and the Green Knight at the moment. It's one of my little projects I've been working on. And from time to time, if the syntax gets really complicated, then I'll use it to help me, sort of formulate a line or whatever. And it's good. I mean, it works. And from everything you've been saying, it sort of shouldn't, if that makes sense.
Yeah. I mean, we've had this view. I mean, English is really a special case because just the vast majority of the training data is English, and the vast majority of the historical training data that these models have ingested is going to be English. So you can really see a sharp drop off. Like even using these models in French or German, they perform substantially worse. Even if you even Chinese, I mean there are other reasons for it because the training data is highly skewed, but on Chinese you get quite even for simple translation task into English, modern Chinese, these models perform quite subparly. So you can't use it as a general translation tool for Chinese, for example. So it's most likely not any kind of innate intelligence or any kind of yeah, super ability to do these kinds of tasks. It's really just a function that for English you have so much more training data to put into this model. What could also happen is maybe there's a modern edition of your text and it realizes that it's reading or there's a normalized modern edition of your text, and it realizes that it's reading the same text in a medieval dialect, and it just picks up the modern edition and outputs the modern edition verbatim. That's entirely possible as well.
That is possible. And in fact, I have picked up some of my students where when I use GPT-0 on their translations, it makes a mapping to a little known edition of Gawain and the Green Knight, a really sort of archaic old edition of the poem. And I wondered about it. And what I tend to do is I'll just say, are you aware of this edition? I don't say this is plagiarized. I'll just say you're aware of this edition. And then suddenly those things don't stop in subsequent editions. So that actually, I can see that. That's interesting, isn't it? Yes. Okay, fine. I mean, the other thing, just out of interest, is also that one of my long-term projects is a scholarly rhyming version of Troilus and Crusade. And again, in that one, sometimes what I'm trying to do is to do as much of a literal translation as I possibly can, preserving the original meter and the word order and things like that. And that's tough. That's hard. And sometimes if I get a line that's very hard, I will then, plug it in and see what it comes up with. And 9 times out of 10, it'll be rubbish, but sometimes it'll be very good. But as far as I know, there is no rhyming edition of Troilus and Crusade that's scholarly. So that's sort of interesting as well. So there's obviously some kind of interpolation going on. But anyway, this was a great talk. I really enjoyed it. Thank you very much.
Thanks.